Hello, I'm Dr. Harper. This video is on operations management, it's scheduling queuing systems lecture. So let's bring up the notes. In scheduling, the supplier and process and customer are going to overlay a logistics model with this input-output process to where you have upstream the purchasing operations, which has to do with sourcing, receiving, the receiving dock, production control, movement of things through the business unit or operations, distribution, quite often it's going to be transportation, and finally demand management or customer relationship management. This is referred to as a logistics model, and essentially logistics just means movement of things. Movement of things from one place to the other. It can be movement of material, movement of people. Some cases it could be movement of money, but here we're talking about movement of material. This can be broken down, and we'll be focusing on the production control part of the logistics model. This can be broken down into scheduling, movement of things, through the job shop, which is a process-focused design, and we'll be looking at sequencing rules, flow diagnostics, Johnson rule, and Gantt charts in this video. You can also look at assembly line. An assembly line would be more of a product-focused design, and that would be the aggregate why-not method with one technique, which is very useful. The other in the service design, another technique, one very common technique, is called cyclical scheduling, which we will not do these last two in this video. This video is focusing on job shop with a single queue through different processes. A single process and two processes in series. Okay, so let's first look at the sequencing rules. Sequencing rules start with something called a queuing system. A queuing system is made up of a queue, which is nothing more than a waiting line, and these circles represent entities within the waiting line. It could be people, it could be jobs, it could be cars, it could be pieces of information trying to be processed. And finally, we have a server. And the server is servicing the different entities. For example, these could be jobs waiting to be processed by a company. These could be people at a waiting line at the teller of a bank, and the server is the teller. These could be pieces of information coming into a switchboard, and the server is the switchboard. And so the N here stands for the number of entities in the queue or the system. N by 1 stands for the number of servers. Now this is just my nomenclature, my definition. There's all different definitions for this. This is just my definition to keep it simple for this lecture. Okay, sequencing rules. What does that mean? When these jobs, let's say these are jobs, when these jobs arrive at the system, the queuing system, suppose they can be ordered any way that we want. Each one of these jobs are going to have different processing time through the server. The server takes a different amount of time to process each job. If we can reorder the number of arrivals, these jobs, if we can reorder them and we can create our own order or sequence, then the rule which we follow to create that sequence or order or schedule is called a sequencing rule. And we'll be looking at 5. But the MPT rule, earliest due date, minimum start date, minimum slack time, and minimum critical ratio. So we'll be looking at 5 of these. Now before I get started with these 5, I'm going to mention a sequencing rule that's not here, that's not part of these 5, but extremely common. FIFO. And that equals first in, first out, okay, and sometimes it's referred to as first come, first served. Another one is LIFO, which is the same as last in, first out. And in my video on my website, I do talk about examples of FIFO, like people waiting in line to be serviced, LIFO, like shipments waiting to be processed. The last one's on the truck is the first one's delivered. So these FIFO and LIFO can be extremely valuable and very important and they are two different sequencing rules that are not here. But when you do have the option of sequencing these, let's look at these 5 sequencing rules, because each of these are very good. They have some properties, characteristics that I want to point out. Okay, let me illustrate these 5 sequencing rules with an example. Suppose I have 4 jobs waiting to be processed here on the server, and I can reorder those 4 jobs any way I want. Along with the jobs, suppose we have something called a processing time. PT is processing time. And suppose this is in days. Job A takes 4 days to do, B takes 6 days to do, 10 days, 18 days. Well, if I can order them from the smallest processing time to the largest processing time, therefore, that would be the order of my MPT schedule. The first job is A, second job is B, third job is C, fourth job is D, because A has the smallest time, B has the next highest time, C has the next highest, D has the next highest. So that's the MPT rule. It's very simple. But as it turns out, the MPT rule has some very strong, important properties, which we'll look at here in this video. The second is the earliest due date. Along with each job, suppose we also had a due date. And this date is the date at which the job is due to leave the system. It's the due date. It's when it's due to leave the system. So these numbers here are dates. And in my video, I describe that these are Julian dates. Usually people are more familiar with Gregorian calendars, where you have January, February, March, April, May with different days within the month and 7 days in a week. But the Julian calendar is just taking like the Gregorian calendar and sequentially numbering the days from 1 on, regardless of the months. So Julian date 63 is a due date. It's the 63rd day of the year. Now, if it's not leap year and we have 28 days in February, then January is 31, February is 28. Okay, that would be 60. So 63 would be March 3rd. And so that's how you go back and forth between Gregorian calendar and Julian calendar, or Julian dates. Okay, well, the earliest due date simply is the smallest one, which is 51. That'll be the first job in the earliest due date schedule. The next highest time is 60. That's the second job. The next highest time is 63. That's the third job. And then 66 is the fourth. So notice the MPT rule and the earliest due date are not the same schedules. MPT is A, B, C, D. Our earliest due date is B, C, then A, then D. Okay, and so if you have just the processing time and all the due dates are the same, you might want to use MPT rule. If you want to take advantage of some of the properties of the MPT rule, you'll use the MPT rule even if the due dates are different. Or if the processing time is the same and the due dates are different, maybe you want to do the earliest due date. Okay, so there's 2 schedules. Pretty simple, straightforward, not difficult. And so the MPT is ABCD, the earliest due date is BC, and then AD. And I just want to comment here, in passing, this is not part of the lecture, well, not part of the course or anything. I did not notice this when I did this, but after I started teaching this, I began to realize that this earliest due date schedule, when you talk about dates, it's very logical. The first 2 is BC, dates. The last 2 is AD, dates. Start with BC and AD. And that's very appropriate if you get my drift. Okay, let's go on. Now, you can combine the processing time and due dates together with a minimum start date. And that's the due date minus the processing time. Very simply, I take the due date, I subtract the processing time, and that's called a start date. So it is a date. But let's interpret this. Well, if I subtract the processing time from the due date, well, this date is the latest date I can start. If I start on that date, which is the processing time in front of the due date, I'll be done right on the due date. So this is the start date to be done right on the due date. If I start earlier than the due date, start date, I'll be early. If I start later than the start date, I'll be late. So the start date is the latest date I can start and not be late. So I take the minimum start date, 45 here, that's B. But the next highest one is 48, that's D. And then C is 50, and then A is 59. And notice the minimum start date is not the same as the MPT or the EDD date. They're different. It's B, D, C, A. So I have 3 different schedules. Okay, closely related, or very similar, or identical actually, to the minimum start date is the minimum slack time. So the slack time here simply is the start date, and I subtract something called the present date. Now the present date, I use the word present, a term present date, to keep it simple. But really the present date is the date on which this project of ABCD starts being processed. That's the very first date at which I should have said beginning date. Maybe I should change that in future lectures or something. But it's the present date at which you're going to start processing. So I say present because you can change all your schedule, but then once the last job comes in, boom, this is the present date at which you create your schedule and start processing. Okay, I subtract, well, suppose my present date is 53. I subtract 53 from the start date. Well, since I'm subtracting the same number from all the start date numbers, then the order will always be the same. So the schedule of these two will always be the same. Here's B, D, C, and A. So why do we have 2 schedules? Because of the diagnostics. The start date is used for scheduling and the slack time is used for analysis. Well, let's interpret the slack time. Since I'm subtracting the present date from the start date, and notice 59 minus 53 is 6, that means the present date is 6 days before the start date happens. So I am 6 days ahead of the start date, or before the start date. So if I start on the present date, I'll be 6 days early. So I can wait wait one time period before I start, and only be five early. So I can wait as many as 6 days before I start job A and not be late. So that's a slack time. It's how much slack you have to start the job relative from the present date to the start date. But notice B, C, and D is negative. Interesting. When you have a negative start date, that just means, if I start today, I'll be 8 days late. If I start today, I'll be 3 days late for C and 5 days late for D. Well, you still have the minimum start date and minimum slack time. So -8 is first, -5 is second, -3 is third, and then 6 is fourth. So notice the only way you can have any job on time or early is scheduling A first. Because if A is scheduled first, it'll be on the present date, it'll be 6 days early. But all the others are going to be late. There's a horrible schedule. horrible scheduling problem. So you'll be a lot of expediting or calling people saying, sorry, it's going to be late. But I devised this just to illustrate the numbers. So the last rule is called the minimum critical ratio rule. And it's a ratio of the due date minus the present date divided by the processing time. The due date minus the present date, for A here, it's 63 minus 53, which is 10, divided by 4 is 2.5. Okay, let's interpret this number before we go on. And once we get all the numbers, notice one's negative. That's the first one. The next highest number is 0.7, that's the second. 0.72 is the third. 2.5 is the fourth. It's the minimum critical ratio. But let's interpret this. The numerator I will call supply time. In other words, the due date when it's due to leave the system in the future, and the present date when you're starting, that time is the time supplied to do the job or get the job done. From the present date to the due date, that's how much time you have to do this job. You divide that by the processing time, how long it takes to do the job. So when you have the supply time divided by the processing time, that's a ratio called the critical rate ratio. So if the supply time and processing time are the same and the ratio is 1, that means if you start on the present date, you'll be done right on the due date. Okay? No, it won't be late. So that's a ratio of 1. But if the supply time is greater than the processing time and the ratio is greater than 1 if you start on the present date, then you'll be done early. Now, if the supply time is less than the processing time and the ratio is less than 1, if you start today, you'll go past that due date and you'll be late. So you have different interpretations. Now, it is possible for the due date and the present date to be the same date. Like, when is it due? It's due today. Oh no. Okay, so that just means you'll have a critical ratio of 0. But notice B here. Notice activity B that I introduced. The due date is 51. The present date is 53. And so some people have said, well, how can you have a present date of 53 and it was due 2 days ago? Well, that's pretty common. It says, oh, here's a job. When's it due? It was due yesterday. Oh, am I just getting it today? Someone's, they didn't send it down. They didn't do this. It was a problem. Okay, so it will be late. It does happen. And it can't be avoided sometimes. It will be late. So you can have a negative critical ratio. So here, you schedule at the minimum critical ratio. The minus is the first one. The next highest is C, then D, and then A. So it's B, C, D, and then A. Now, the critical ratio of all of these probably is the most flexible and the most powerful of these critical ratios. And here's why. Well, I have the numerator, which is supply time. I have the denominator, which is processing time. Well, what that implies is that the smaller the supply time, the smaller the critical ratio, and you want that to schedule that early. The larger the processing times, the smaller the critical ratio, the longer the processing times, you want to move those to the end of the schedule. So that's the concept, or that's the criteria with these two pieces of information. But that implies that, well, you can have anything in the numerator and anything in the denominator depending on your criteria for your particular problem. It's very flexible. You can use this for all different kind of scheduling problems, scheduling challenges, scheduling protocols and rules. Just say, well, if the number is small, that's good. That should be early in the schedule. Put it in the numerator. If large is not good, that should be later. Put it in the denominator. For example, suppose you want, they come in with different revenues. They're all the same cost, but some will have different revenues. Well, you want the one with the highest revenue to be early, because that way, the sooner it gets out, the first ones you do are going to have a higher revenue, and that'll really be a good cash flow. So the greater the revenue, the better. Where does it go? It goes in denominator, because then the ratio is smaller and it'll be done first. But then priorities. Because suppose you had a priority 1, 2, 3. Priority 1 is more important than priority 2. Smaller is better. Where does that go? In the numerator. Okay, so you can tailor make this to pretty much any type of problem. When you have data, when you have parameters, and a practical suggestion here is that never use more than 2 or 3 in the numerator or even the denominator. Keep the number fairly small. In other words, you take the different criteria, the parameters you have, the data you have, and do a Pareto analysis. Which one is more important? And if you just have one number in the numerator and denominator, that's perfectly fine. 2 and 2, 2 and 1, 1 and 2. Don't go more than 3, because then it gets confusing. Okay, they're just some practical issues. So now we have 5 different sequencing rules, 4 different schedules. Okay, well, let's look at some diagnostics. There's a lot of diagnostics. A very common diagnostic is flow diagnostic. So the flow of a job is the number of days, or the amount of time a job spends in the queue and the server, or it spends in the entire system. In other words, suppose a job spends 2 days in the queue, 1 day in the server, the flow is 3. If it spends 1 day in the queue and then 3 days in the server, the flow time is 4. So the flow is how much time it spends in the system. And in the system, it's either going to be in the queue or the server. And you add those times up, that's flow. Okay, the flow of a job is the number of days a job is in the system. So let's do the flow for the MPT schedule. So here's the MPT schedule, ABCD, 4, 6, 10, 18. So you take the flow of the first one, it's going to be 4. Okay, the second one okay, first of all, the job A, the first job in any schedule will have a queue time of 0 by definition. Doesn't have to wait, it's the first job. Nothing in front of it to wait for. So the queue time is 0, the processing time is 4, 0 plus 4 is 4. Now B has a processing time of 6 in the server. The queue time is going to be 4 because B has to wait until A is done. And A spends 4 days in the system before it leaves. So 4 is the queue time of B. So 4 plus 6 is 10. So C has a processing time of 10. It has a queue time of 10 up here. 10 plus 10 is 20. So D here has a queue time of 20 because it has to wait for C to completely leave the system before it can be processed because it's behind C. And then 18 days in the server. So 20 plus 18 is 38. So the flow of the last job in a schedule is the total processing time. So the total processing time of this schedule is 38 days. Another word for total processing time quite often is the make span. The make span of this project. The total processing time of a project, or the make span of a project, is 38 days. In other words, if I add all these up, I get 38. But these are the flow. The flow of the last job in a schedule is the same as the total processing time. But if I add up all the flow, this is the total flow in the schedule. Well, the total flow is 72. Now, again, my video describes an interpretation of flow. But flow is a diagnostic. It's a measure of weight, of load, of maintenance requirements, of cost. My example I have is cost in the video. And so my video presentation really talks about different applications, interpretations of flow. So I encourage you to see that, to watch that. Okay, so let's summarize. The total processing time, or make span, is 38. The total flow is 72. Now watch what I do. If I take 72, if I divide by the number of jobs, it's flow per job, right? It's the average flow per job. But remember, what's a flow? Flow is the time spent in the system. So on the average, a job spends 18 days in the system on the average. Some more, well, notice up here, none of them spend 18 days. It's just an average. It's a metric. It's a diagnostic. So on the average, a job spends 18 days. Well, how many jobs per day? Well, if it takes 72 and divide by the actual processing time of 38, well, the average jobs per day is on the average, 1.9 jobs per day. So notice 72 is in the numerator on each one of these, total flow. So the total flow is in all three of these metrics. Now, property, a very important property. And I explain this and I demonstrate it in the video, but to minimize the total flow, the minimum total flow will always be the MPT schedule. The MPT schedule will always generate a minimum flow. So notice the earliest due date, 72, goes up to 80. The mean start date, mean slack time is 102. Mean critical ratio is 94. So the minimum flow of any schedule is attained by using the MPT rule. Now, one of the other rules may be the minimum too, but MPT will always be minimum. Okay. Therefore, if I divide by 4, which is constant, and also the processing time of 38, 38 is always the processing time, and an n by 1 system is always the same regardless of the schedule. Interesting. Good properties to remember. The processing time could be said to be independent of the schedule. It doesn't matter what the schedules are, the processing time is always the same. The flow time is dependent on the schedules. Different schedules will give you different flow times. Can give you different flow times. Okay? So, to minimize total flow, to minimize average flow per job, to minimize average jobs per day, use the MPT rule. To minimize the total processing time, doesn't matter which one you use, they're all minimum. They're all going to be the same. Okay, so close related to flow is something called lateness of a schedule, or the lateness of a job being late. So the present date, remember, is 53. Now, the date of completion will be the present date at which you start the actual processing, plus the flow of each job. Because the flow is how many days a job is in the system. So the number of days times the present date will give you the date at which it's completed. So for the MPT rule, here's my processing time, here's the flow, here's the present date, and there's my date of completion, just the sum of those two. I can compare that with my due date. So I bring down the due dates. Now, if the date of completion is greater than the due date, then it's going to be late. If the date of completion is less than the due date, it's going to be early. So if I take the date of completion and I subtract the due date, what I get is the lateness. And notice 57 minus 63 is a minus 6. Well, it's not late 6 days, it's early 6 days. Well, notice that 6 days early is the same up here as the slack time of job A. Okay, but these others then are late. 12 days, 13 days, 25 days. These are the lateness. I add this all up, and the total lateness of the MPT schedule is 44. Now notice I incorporated the minus 6. Some people don't. Some people do. Some people only look at just the ones that are positive. So people do different things. For this course, I just add them all together. Okay. I do the same thing for the earliest due date, the minimum start date and slack time, and the minimum critical ratio. And notice this is minimized right here with 44. Okay. Not always the case, but it will. In this case, it's the minimum. Okay. So there's lateness. Now let's move from an n by 1 system to an n by 2 system. So now we have 2 servers in series. Since I have 2 servers, I have 2 processing times. So A, B, C, and D are processed on server 1 and server 2 different times. Okay, now there's some rules here. And the rule is, once you have your sequencing rule, once you have your schedule, and by the way, this is the first one, second one, third one, fourth one. Okay, that's the order. Once you have that order, then the first one is serviced here, but then once this is serviced, then service 2 is idle. Well, the second job will not get out of line to go to server 2. It stays in line. And then server 1 will finish with the first job. It goes to server 2. And then the second job can be serviced on service 1. And so you can have both of these being serviced operative at the same time. Okay, the first job is in the server 2 and the second job server 1. Now at this point, 2 things can happen. Either server 2 can be finished before server 1, at which case it stays idle. Or server 1 can be done before server 2, at which case the third job is in here processed, and that second job waits in a queue right here in front of server 2. So the queue time could be in front of server 1, and there's another queue time in front of server 2. I didn't put it here because to begin with you don't have a queue to begin with, but it could within the processing time of the project. Okay. So remember before, in an n/1 system, the total processing time is independent of a schedule in an n/1 queuing system. In other words, like I said up here, the processing time is always the same regardless of the schedule, so it's independent. However, for an n/2 system, the total processing time is dependent on a schedule in an n/2 system queuing system. So the processing time does change with the different schedules. The sequencing rule to minimize the total processing time in an n/2 queuing system is something called Johnson's rule. So Johnson's rule is a sequencing rule for an n/2 system that minimizes the total processing time of a project. So Johnson's rule is essentially an algorithm. It's a 3-step algorithm, and these are the 3 steps. So what I want to do is actually illustrate and go through these 3 steps and show how it's done. Okay, step 1, find the minimum processing time. Okay, we come through here, and what this means is find the minimum time of all the times. 4, 3, 2, 6, 4, 1, 5, 4. The minimum time is right here. And actually, let me come up here and let me shade that in so we can actually see it. There we go. The minimum time is 1 of all 8 times. Step 2. Well, if this minimum time is on the last server, in this case the second server, then schedule C in the last available position. And there it is. Now, if this minimum time had been on the first server, it's not. But if it had, I would have scheduled C in the first available position. But since this minimum time is on the last server, then I schedule C in the last available position, the 4th job. So now that's step 2. Step 3, I eliminate C from the problem. I go back to step 1 with the 3 remaining jobs and 6 remaining times, and I do it again. That's the first iteration. Step 1, 2, step 2, step 3 of the first iteration. Second iteration. Of the 6 remaining times, 4, 3, 2, 6, 5, 4, the minimum time is 2. Let's shade that in. Notice this minimum time is on the first server. Therefore, I'm going to schedule B in the first available position, which is the first job. Step 3, I'll eliminate B, go back to step 1 with the 2 remaining jobs and 4 remaining times. So let's do that. Okay, of the 4 remaining times, 4, 3, 5, 4, the minimum time is 3. Let me shade that in. Now this time, the minimum time for A is on the last server. Therefore, I will schedule A in the last available position, which is the 3rd job. Now, if this minimum time had been on the first server, it's not. But if it had, I would have scheduled A in the first available position, which is the 2nd job. But since it's in the last server, then A is in the last available position, which is the 3rd job. So now that I've scheduled A, step 3 says eliminate A. You only have 1 job left, 1 space left. So then BDAC, the Johnson rule scheduled in as BDAC to minimize the total processing time. And that's Johnson rule algorithm, Johnson rule concept. Okay, but notice, let me point something out that some people get confused on. I say the Johnson rule schedule is BDAC. Well, BDAC, let me do it this way, come across here, 1, 2, 3, 4, right? Okay, and essentially, let me do this, bring this over here. B is a first job, D is a second job, A is a third job, and C is a fourth job. Because when you read in a sentence, it goes from left to right, 1, 2, 3, 4. Now the reason I'm making a point of this is in the graph up here, let me put it under here, we're going to have BDAC, C, A, D, B. And here's B, D, A, C. B is the first job, D is the second, A is the third job, C is the fourth job. 1, 2, 3, 4 goes the other way because we're moving in this direction. So be very careful that you understand the order in which these things are being represented, either in a graph or in a sentence. Well, there's two things I want to point out here. Two very important things I want to point out. The first thing is the concept of the Johnson's rule, characteristic of minimum processing time, the concept. And that is shorter times on the second server here, move those to the end of the schedule. Shorter times on the first server, move those to the beginning of the schedule. Now that simple concept, this illustrates it here, and I demonstrate it in the video. That simple concept can be used even when you don't have an n/2 system. It can be used in any type of multiple stage queuing system. Suppose you had 20 jobs on 4 machines. Well, you can say, I'm going to add the first 2, the last 2, do Johnson's rule. Or just do the first one and the fourth and do Johnson's rule. And then the middle 50% do the second and third machine server. So you can just use that concept even when you don't have a specific n/2 system. Okay, and it turns out it's not perfect, it's not optimal, but it's a very good system. It's a very good schedule. Now the second thing I want to point out is you may have thought of this. What if there's a tie? What do you do if there's a tie? Like right here, what if both of these were 3? What if that was a 3 and that was a 3? Then what do you do? Well, A here, does A go in the third job or in the second job? You can have different schedules. Well, there's 2 answers to that question. The first answer is, I'll be very careful not to do that in this course to keep it simple, so you can understand Johnson's rule. Okay, but the second one is more realistic. It does happen. And so when it does happen, it moves you into a different type of scheduling algorithm, different type of scheduling considerations, a different type of scheduling analysis. For example, one approach might be just arbitrarily pick one, get a schedule, go back and pick the other, get another schedule, compare the two with a flow diagnostic and see which one you want. That's kind of brute force, but there's all different ways of handling ties. That's why we don't cover them in this lecture. Okay, so there's my Johnson rule schedule, BDAC, very useful, popular, and usually in processing within assembly lines or processing, a very important rule. Okay, next, let's look at Gantt charts. Gantt charts is simply a graphical representation of these schedules that we're looking at. So let's look at it. Let's look at an n/2 system. So here's my n/2 system, and here's my processing times over here. So let me, and all a Gantt chart is a linear representation graph of a schedule. So let me Gantt out or graph 2 schedules, a FIFO schedule ABCD and the Johnson rule schedule BDAC. Let me show you how the Gantt chart works. Okay, first of all, the FIFO schedule. Here's FIFO. Let me bring the jobs ABCD with a processing time on server 1, processing time on server 2, bring it down, and there it is. Okay, now as I go through here, I say, okay, I'm going to represent on a timeline 1 through 20 here. This is 20 days. On a timeline, I'm going to go through here and represent graphically the days on server 1 and the days on server 2 for each of the jobs. Let's look at A. So for A here, I'm letting 1 represent the time on server 1. So A spends 4 days on server 1, so I'm putting a 1, 1, 1, 1 4 times. 1, 2, 3, 4. Now some people put a 1, some people put an X, some people put an arrow. You can put a figure in there or a circle. Some people put an arrow. Some people put an emoji or whatever you want to put in there. But anyway, you're representing a timeline. So there's the 4 days. So job A on server 1 takes 4 days. And then it moves to server 2 for 3 days. Well, time on server 2 I'm going to be represented with the number 2. So for 3 days, 1, 2, 3. And so notice the job A has no queue time at the beginning and no queue time. Once it gets done, it goes directly to the second server. So there's no queue time here and there's no queue time here. So job A, there's no queue time on the first job on any schedule. There's no queue time. Okay, what about the second job? Well, there's a rule. The rule is that a server can only service one job at a time. So for the first server here, B has to wait until the first server is available, and then it can process for 2 days. Boom, boom. So this right here represents queue time. B waiting in a queue for server 1 to be available. So that's a queue time in front of server 1 for 4 days. And then it goes to server 1 for 2 days, 1, 2. But then when it's finished on server 2, we can see here it is done here. But notice server 2 is busy processing A. So a server 2 cannot process 2 jobs at the same time. It's processing A here. So B has to wait here, has to wait in a queue in front of server 2 here for, let's see, 1 day. So this is the queue time in front of server 2. So B here has a 4-day queue time in front of server 1, a 1-day queue time in front of server 2. So the total queue of B is 4 plus 1 is 5 days. It's 5 days. So now we're going to have total queue is a Q1 in front of server 1, Q2 in front of server 2. Both is a total queue of a job. But then it goes to server 2 for 6 days, 1, 2, 3, 4, 5, 6, and there we go. And so now you can tell job A has a flow of 7, because when it gets done, it leaves the system. B has a flow of 13. Remember, the flow is the number of days a job spends in the system, which is the queue time plus the processing time. Right here, the queue time, 4 plus 1 is 5. The processing time, 6 plus 2 is 8. 5 plus 8 is 13. It still applies in an n/2 system. Job C. Job C is going to wait until the first server is done with A, done with B. Then it can process C for 4 days. 1, 2, 3, 4. Then it goes directly to the second server. But notice the second server is busy for 3 days. So now C spends 3 days in a queue in front of the server 2 until server 2 is available, and then then the processing time is 1 day, so it spends 1 day, and then the flow time is 14. So if the flow time is 14, and here the processing time is 4 plus 1 is 5, then what's the queue time have to be? 14 minus 5 is 9. And we could see here this is 6 plus 3 is 9. Now D has to wait for the first server to be done with A, to be done with B, to be done with C, and then it processes D for 5 days, 1, 2, 3, 4, 5. When it gets done, it goes directly to the second server. And notice the second server is available, so there's no queue time here for 4 days. For 4 days. 1, 2, 3, 4. And now the flow time of D is 19. But the flow time of the last job in a schedule is the total processing time of the project, or the schedule, or the make span of the schedule. So it takes 19 days to do. So now the Gantt chart is very powerful. It tells you a lot of information. It tells you the time of completion of the project, or the make span of the project, or the total time of completion of the schedule. It tells you the flow of every job in the schedule. It tells you the processing time. It tells you the queue time of a job. But it tells you something else too. Remember, a server can only process one job at a time. Right here, the first 4 days, notice that 2 is idle because 2 is not processing anything. It's got to wait for A to be done on server 1. So 2 is idle. 1 is busy. But once one starts, notice 1 is busy, busy, busy. 1 will be busy until it's completed all of its jobs. But then once it's done, then it's sitting idle for 4 days until the last job is done. Well, notice, look at days 14, 15, and 16. Day 14, server 2 is busy and server 1 is busy. Both servers are busy. So that's the best situation because both servers are processing something, and that's why the processing time can be minimized with an n/2 system when you have Johnson's rule, because they're trying to optimize the parallelism of the processing of servers 1 and 2. But look at day 15. Only 1 is being processed, 2 is idle. It's not doing anything. Day 16, 2 is busy and 1 is idle. So in your Gantt chart, you can also measure the idle time of the servers. And the Gantt chart will show that to you. Well, in addition to the scheduling part of a Gantt chart, you can also use a Gantt chart for management. This is a progress report of work actually performed. So, for example, suppose that this is a schedule. This is a schedule. You haven't started working yet. But then once you start working, this is just a schedule. Sometimes you're ahead of schedule, sometimes you're behind schedule, sometimes you're on schedule. So down here is the work that's actually being performed. So day 5. Let's look at day 5 here. 5 days into this thing. Okay. First of all, job A, server 1 reports 100% done with A, 50% done with B, and server 2 says 0% completed. Okay. Well, at the end of day 5, notice server 1 should be completely done with A, and it is. It should be 50% done with B, 1 out of 2, here's B, and it is. So server 1 is right on schedule. So over here, server 1, I say, is on schedule. But what about server 2? Well, at the end of day 5, server 2 should have 1 out of 3 days done. It reports 0. So it's 1 day behind schedule. So server 2 is 1 day behind schedule. So this chart here can tell you after 5 days who's on schedule, who's ahead of schedule, who's behind schedule. It's a summary. What about 10 days? Okay, 10 days. Now what happens? Well, after 10 days, 1 reports A and B 100% done, C is 75% done, and server 2 reports A is 100% done, B is 83% done. Well, just as before, server 1 has done more work than server 2. So here's where some problems come. Managers, companies, people who don't understand operations or scheduling, who don't understand queuing systems, if you have people managing operations who are not managers, who are not MBAs or understand scheduling, they'll say, oh yeah, server 1 again is ahead of server 2. Oh, okay, well, they're doing more work than 2. They're better than 2. 1 is better than 2. 1 should be promoted. 2 should be penalized. Let's just fire 2 because they're behind twice. Until you match that up with a schedule. Let's look at the schedule. Well, server 1 should be 100% done with A, 100% done with B, 100% done with C. It's only 75% done with C, so it's 1 day behind schedule. So yeah, one has done more work, but because of the schedule or the requirements of your queuing system, it's really behind schedule. What about server 2? Well, after 10 days, server 2 should be 100% done with A, and right here should be 50% done with B, 3 out of 6 days. It reports 100% and 83%, which is 5 out of 6 days. 5 out of 6 is 83%. So 2 is really 2 days ahead of schedule. So what I'm trying to emphasize here is that the Gantt chart is a very powerful tool, a very useful tool. And people that don't use it, they say, oh, I can do it without it. And they go, oh, okay, well, one should be rewarded when they are behind schedule and not they're not on schedule. 2 should be penalized when they're ahead of schedule. It's just the opposite. And that opposite amount of management, poor management, can happen, does happen all the time. And again, that's why you need people with a business degree, understanding business, doing scheduling, who apply the schedule appropriately and correctly. Okay, so then you can manage people. So when they're behind schedule, you don't penalize them, you support them, you help them. So what can you do to get them back online? Okay. Now, the last thing I want to cover here is the Gantt chart of Johnson's rule. I'm using this to illustrate why Johnson rule works. Remember, the concept of Johnson rule is the smaller times on the first server is early in the schedule. The smaller times of the last server is later in the schedule. Why does that work? Well, let me illustrate. Right here, let's see here. Let me start by simply saying, let's just ignore the second server. How long does it take the first server to process all these jobs? Well, let's see here. There's the B, there's a first job, and there's a second right there, and there's a third, and there's a fourth. It takes a total of 15 days for the first server to process all these jobs. Okay, well, how long does it take FIFO? Well, let's see. Here's the first one, here's the second one, here's the third one, here's the fourth one. It also takes 15 days. It's the same. Will it always be the same? The answer is yes. Because if you eliminate the second server, this is an n/1 system. And the total processing time is independent of the schedule. It doesn't matter what schedule you have here. The processing time through the first server will always be the same amount of time. So if that's true, doesn't matter what order you put these in, it's always going to be 15. It's always going to be the same time here when the first server is done. Then when that's done, what time do you want in the last server? You want the minimum amount of time right there. You want the lowest time right there. So this is 1 day. So you want the lowest time on the last server at the end, because once the first server is done, whatever time this is, that'll pull the time of completion of the whole project up to that minimum. So you want that to be a minimum. The next highest is here. The next highest is here to make sure they don't go over. Okay, that's that concept. What about the other? The minimum time on the first server is early in the schedule. Well, that's pretty simple as well. The shorter that time, the faster the second server can start processing. The value of an n/2 system is both servers being processing jobs at the same time. So the shorter this time, the faster the second server can start processing these jobs. Okay, but also you want the longer times here and the shorter times here for the second rule, for the shorter times at the end of the schedule. So you have short here, long here, short here, long here. That inverse is exactly what you do in Johnson's rule to minimize the time. And so that concept can be proven in a proof. We don't get into proofs in this course. But even though if you don't have an n/2 system, but you have processes in series, you can use that concept. May not be optimal, but it'll be very good. You may not go 100% of the way to optimality, but this type of concept you can go 80, 90% of the way, and it's very good. And that last 10, 5, 10, 15%, it's not worth your time and effort. So this concept is very practical. Okay, and people use it quite a bit. That's all I have for this lecture in scheduling, queuing systems with a single server and 2 servers in series. That's all I have. Between now and the next time I see you, I want to urge everyone to be safe and take care.